Finally, we're going to talk about metapopulations. So far, all of the models that we've talked about are closed populations. And that means they can only add individuals through birth and lose individuals through death. Now, in the beginning, I said there's other ways that you can add individuals and another way that you can lose individuals, namely immigration and emigration. When you have an open population, you can add individuals through immigration and birth, and you can lose individuals through death and emigration. Remember, emigration has one M. So these are called metapopulations. Now, to be clear, all of these models were all based on one model. And if you want to look up the derivation of that model, it's the exponential growth model. Whenever you make a model, you have a series of assumptions. And you need to have those assumptions in order to limit the parameters so that you can actually make the model work. And what all of the models that we've been looking at do is slowly relax those assumptions. One of the assumptions of the exponential growth model is that unlimited resources. If you relax that assumption and keep all the others the same, you get logistic growth. Another assumption of the exponential model is that everyone instantaneously gives birth after reproduces after they're born. You relax that and you get age-structured growth. One of the assumptions of the exponential model is immigration, no immigration, no emigration. You relax that and then you get metapopulations. So I'm not showing you all of the models and the derivations, but if they all are very logically flow from one another. These are also highly mathematical models, so I'm trying to simplify them as much as possible. And now these words, immigration and emigration, I just want to go over them really quickly. Immigration means that if you're an immigrant, you're coming in. If you're an emigrant or you're emigrating, you're leaving. So I could immigrate into Canada, or I could emigrate out of the United States. All right, so metapopulations is a theory that actually was developed out of a theory that we're going to learn later on this semester. So again, in a closed population, which is what we've been talking about, the change in the population number equals births minus deaths. In an open population, which is metapopulations, the change in the birth rate, the change in the number in the population equals the number of births plus the number of immigrants minus the number of deaths plus the number of immigrants. Remember, when these models, capital letters mean numbers of individuals and small letters mean rates. That's actually not so important for you to know, but just if you're wondering why sometimes we have big letters and sometimes we have little letters. So metapopulations. So far we've been talking about independent populations. Remember, species are made up of groups of populations. And we've been talking about them as if they're distinct. Metapopulations are linked populations, so they're not really truly different populations. They're what we call subpopulations. They actually have a bunch of different names. We can call them subpopulations, we can call them patches, but it's all the same thing. They're not independent populations, and the reason for that is that they're linked. And there's a lot of dispersal among the different patches or subpopulations. It doesn't mean that every individual subpopulation can get to directly every other one, but indirectly at least they can get to every other one. So this is a picture of Alaskan lakes that are sometimes connected, sometimes not. And so individuals freely move among the lakes. Migratory animals we can talk about as metapopulations, a lot of different organisms. And one of the conservation values of metapopulations is that as we as humans are increasingly fragmenting our environment, we're creating metapopulations everywhere. So it's important for us to really understand this theory. I also want to say this theory has been overused a lot, but it does have a lot of use in conservation biology. So a metapopulation is a population of populations. It's a group of local populations or subpopulations linked by immigration and emigration. Subpopulations interact within a larger region. So we call this the region or the home population. Each one of these are subpopulations. Now, some of them are occupied and some are not. In order to truly be a metapopulation, there has to be a high risk of extinction so that any one subpopulation can go extinct pretty easily. But because they're all linked, that the chances of them actually becoming repopulated are pretty high. So we call this the local populations or the subpopulations, and then this whole thing is the regional population. So what happens is that there's a high risk of extinction in any one of these, but because they're linked, there is regionally a very high risk of perpetuation. Like there's a low risk of regional extinction, because basically what you do is you're spreading the risk. So you have a high individual rate of extinction, but because you can put individuals from one to the other regionally, the chance of extinction is very low. And now this graph is, I know it can be a little confusing. This is actually from the original models. And it's a different kind of graph than we've been looking at. It's more of what we call a state space graph. And so what it's not even that. It's a different kind of graph. What it's showing is the probability of local extinction or any one subpopulation going extinct versus the probability of regional persistence, meaning the whole metapopulation persists. If you only have one, each one of these lines represents a different number of subpopulations. So that's what X is. So here X is 1, so we only have one subpopulation. In essence, everything we've been looking at so far. And if you have 100% probability of local extinction, a 0% probability of local extinction, you have 100% probability of regional persistence, right? Because you only have one population. And then it's just a linear function. But this is a mathematical model, and we're not going through the mathematics of it. But if you start to change around the number of subpopulations, what quickly happens is that the probability of regional persistence gets favored over time. And by the time you're at 16 populations, you have a pretty much 100% probability of regional persistence, even up to almost 80% probability of each subpopulation going extinct. And that's why these are so stable and such good things in conservation. So there's a lot of dynamics for metapopulations. We're not going to go into too many of them, but basically what you're looking at when you look at these dynamics is what is controlling the amount of immigration, emigration, persistence, extinction. One of the big factors that controls whether a patch will be occupied or a subpopulation have individuals in it is going to be the distance between the patches. This actually is pretty obvious if you think about it. So what this is basically saying is here, this is for California gnatcatchers, which is this bird right here. This is the dispersal distance, which means it's the distance between the subpopulations. This is the proportion of individuals in each subpopulation. Oops. What you can see here is that when the dispersal distance or the distance between the subpopulations is low, they're more likely to be occupied. And that's just because they're easier to get to. The farther apart they are, the harder it is to get to. And so you're less likely to have individuals in that patch. It actually makes sense logically. Another factor which governs metapopulations and their regional persistence is going to be patch size and quality. So the patch is the physical space. The subpopulation refers to the individuals. And so let's just look at recruitment here in Florida scrub lizards. And so you can see that the bigger the patch size, which is here on the x-axis, the more individuals that'll be in the patch. And there's a couple reasons for that. One, it's bigger, so it's easier to find. But also, the bigger the patch or the bigger the area, there's more what we call heterogeneous space, which means there's more microclimates, basically. So there's more places for these individuals to hide or to find just the right climate that they can survive whatever the environment throws at them. So the larger the patch, the more heterogeneous. So you have a lower risk of extinction. You can find favorable conditions somewhere in that patch. One way that these metapopulations, or this theory of metapopulations, has been used is something called source sink dynamics. And this really is heavily used in conservation, where we look at what is the source population or the source subpopulation, or that subpopulation where the births are greater than the deaths. So they're supplying individuals to other subpopulations versus the sinks. The sink is a really low quality patch, and the births are less than the deaths. And the only reason that you have any individuals in that patch is because they're emigrating in. And so when we look at sources and sinks, if we had a larger population, say, and your task was to increase the population growth or just to maintain that subpopulation or that metapopulation, you might want to identify which are your sources, which are your sinks, and put your money more into the sources and less into the sinks. So let's see, the concept is used in conservation biology and when designing preserves, restoration sites, etc. It can be very important.